So SYCL I'll cover in a couple of parts, where in the first section, it'll be a brief overview what SYCL is, how you could use it on a test program, and run it on one of the machines that was allocated for this workshop. After post-lunch, we could go over some examples to just motivate you with a brand new programming model. I'll show you how CUDA looks like, which I guess most of you are familiar with, and how that would look like in SYCL, because that would make the syntax and the programming heuristics comparable and at least easy to digest. So before I get in, how many of you are Fortran programmers? I'm sorry for today. Yeah, Cocos, SYCL, and the upcoming session, Raja. It's all mostly driven by C++. I hope this is some learning experience and some information. And how many of you are CUDA programmers or use CUDA libraries? That's quite a bit. And who use it for machine learning purposes? Quite few. So this programming model is mostly driven by HPC applications, but now has gone traction for ML, AI applications as well. So moving forward, what is SYCL? So SYCL is not like a programming model like CUDA or something. It's more of a language specification like C++. So it's a language specification which the vendors take it and write their own compilers, develop their own extensions. So it's a specification and not a programming model. So my title was wrong. So it mostly looks like OpenCL bindings. If you look at the names from SYCL, they mostly look like OpenCL. And the major point here with the SYCL is it's a single C++ source file. So you could have both the host code and the device code. So people who are familiar with CUDA, you would write a main program in .c or .cpp, but your device code lives in .cu in most of the cases, in very simple cases, right? So you have host code and the device code in two separate files, and then you use two different compilers, build the object files, link them, and that business goes that way. So in SYCL, you have a single C++ source file where you could have both the device code and the host code coexisting. And one important thing here is the memory model. So in CUDA, you have device memory, host memory, right? So similarly, we have the same infrastructure in SYCL. And more importantly, SYCL is driven by industry. So it's not an academic project. It's mostly driven by industry. Kronos Group, which is the group that is driving Vulkan libraries, OpenCL. So that is the caretaker of SYCL per se. So coming back to the memory models, you have two different memory models you could choose from. One is USM. I'll come into it more detail later. One is USM, which is called Unified Shared Memory. So each term has a specific meaning. Unified, which means both host and device can have access or can see the memory. Shared, it's you know the shared memory, right? You have a pointer which is valid both on host and device from the unified virtual memory addressing from CUDA and so on. So it's that sort of meaning behind USM. And there is something called as buffers, which is just a different data structure for memory model in SYCL. So asynchronous programming, I mean, that's where the entire heterogeneous programming relies on and has roots to CUDA. It simply means that one could overlap computations and data transfers. And that's how the HPC applications are mostly written, and people are still striving today to take a leverage of that. So it's asynchronous programming, which means you could overlap both computations and data transfers. And on top of it, you could even overlap a host side computation. So you have 3 options in there. So the SYCL programming model or the specification gives you that advantage. And last 2 are the most important things, why industry is mostly interested in it, and even the academia, is the portability. So first, it was started as an approach for Intel's exascale machine called Aurora coming up at Argonne. But after that, SYCL has gained traction so much that it can now run on NVIDIA and AMD GPUs as well. So it runs on all 3 vendor platforms using SYCL, which should bring you back memories from OpenCL, right? It should run on all 3 platforms. So SYCL has that capability to run on all 3 hardware platforms. And today, if time permits, we would run some simple examples on Perlmutter, which is the machine that you should all have access to. And the instructions are on the slides that are posted, how to log in, how to get a node, and how to run a simple test case. So that's the story with the portability and productivity. Of course, you don't have to maintain different versions throughout the years. So as we have heard from Damien in Cocos, people do spend quite a bit of time trying to rewrite code as you get the new programming model, new machine, even a simple change in the programming model. One would spend quite a bit of time trying to get it working. So that's the reason behind productivity here. So you have SYCL with the minimal effort. I'm not saying no effort here. With the minimal effort relatively, you could make it, you could have a productive time. And coming to the motivation, as I said, SYCL is a programming, is a specification, sorry. And one API is the Intel's implementation of that specification. So SYCL came up with certain guidelines, and that's the specification. And Intel has come up with a one API implementation of that SYCL. So when you hear DPC++ from now on, DPC++ is nothing but data parallel C++, or in other words, it's nothing but SYCL. So it's just a combination of C++, the standard C++, and the SYCL specifications that the Kronos group has came up with. So one API is just an implementation of these two combined. So it's mostly based on modern C++. So you have the familiar lambdas features, and more importantly, it has to be C+ 17 compliant. So that's a restriction, or more possibly a limitation, and it can loosely support any advanced features as well from 20 or 23 standards. And again, it's a standard-based cross architecture. So there's no just the programming model that is locked to a specific hardware like CUDA, so which you can run it on only NVIDIA GPUs, right? So this is cross architecture dependent. And I have missed one point, that you could run SYCL on all three vendor hardware's GPUs. But more importantly, it was first designed to be run on CPUs to use all the cores as a parallel programming strategy. And one more thing that has gained traction is the FPGA architectures. So people who had access to FPGAs used to write code in OpenCL, but now with SYCL, you have all these vendors, all these hardware architectures with just a simple C++ styled programming model to use that could be run on all these machines. SYCL extensions. So you've seen that one API implementation of SYCL is nothing but a combination of C++ and some SYCL extensions. These are first motivated by a vendor. So vendor comes up with some extensions and puts it into a SYCL. And sometimes if it is too good, SYCL committee takes it and ratifies it as a standard. That's the process. So I'll be talking about the SYCL extensions that Intel has come up with in its one API implementation. The most important thing behind this extensions from a vendor is, as you keep using it and as you keep comparing it with the existing programming models, the most important one is CUDA. So when you are exposed to SYCL like this, you first ask question like, oh, how would this equate in CUDA? How would this memory model or an execution strategy look like in CUDA, right? So SYCL, people were trying to do comparisons, and most of us have CUDA codes. So obviously we will look at taking that and then porting it to SYCL, right? So all these caused the motivations behind creating these extensions. So as said, like the process is vendor writes their extensions, puts it into a specification if it's too good. So this is the general chart of the portable programming model for SYCL. So it's basically a C++ based intranode parallelism, same as CUDA. So it's a specification I said several times, and it has to be compliant with C++ 17 standards, sorry. So it has a cross-platform abstraction layers and heavily backed by industry and all that goodies. So you could see from this chart that how C++ libraries, the standard C++ libraries, machine learning frameworks, and all these could use the SYCL compiler to just run on any hardware. So if you're choosing CPU, GPU, FPGAs, you could just run it on OpenCL. So OpenCL is a backend which runs. So you just write in the code in SYCL, and that would just run on all these machines. So yeah, there's tons of applications you can see here, SYCL, BLAS, and Eigen. If you have used it, there is a SYCL plugin into that. The C++ STL library, the standard template library, has SYCL extensions to it. So yeah, 1DNN is deep neural network library. So there is quite a bit of projects that are ongoing that surrounds around SYCL. So who are the players currently? So there are three major players who are developing compilers which are performant, I would say. The first one is Intel, and the one API, DPC++, is what I'm talking about earlier. It's DPC++ is nothing but data parallel C++ based out of LLVM. And there is a CodePlay from UK. They do develop a similar infrastructure. And there is an academic project from University of Heidelberg called HipSYCL. So these three are the most notable players in developing SYCL compilers and then testing it on different hardwares. So today we'll be mostly focused on using this LLVM-based compilers and running it on NVIDIA GPUs on Perlmutter. So yeah, as you can see, just using this compiler with the SYCL, you could run it on NVIDIA, AMD, and Intel GPUs if you have access to it. So talking about Perlmutter, so we will use NERSC's Perlmutter as the testbed for today's exercise if time permits. So there was initially collaboration between Argonne, NERSC, and CodePlay to come up, design the compilers to use it on A100s. So you already have NVIDIA compilers, NVCC, CUDA codes, but we don't have the necessary compilers for SYCL, right? So it was a collaboration, and things were pretty good, and we were able to test extensively using SYCL on these large-scale LCF machines. So, and this is just the scope of the work and the players and the backends that it supports. So I'll talk mostly about in the first half before lunch the fundamental units of SYCL, and that should and draw conclusions of how does it compare to CUDA for easier understanding. So you have a device. In our case, it's mostly a GPU. When I say device, so you have SYCL that needs to interact with the device, and in CUDA you do a CUDA set device, right? So and you give a device ID. That's how you activate a CUDA device. So SYCL do have the same heuristics. One important thing here is, how many of you have heard of MIG mode in NVIDIA architectures, where you chop the A100 into several pieces and then launch ML-based applications? Yeah. So if you're not using a A100 very efficiently with a single executable, what you can do is you can partition the A100 for its memory and the resources, and then use it as a small machines. That's nothing but a MIG mode, multi-instance GPU mode. So you can run multiple instances by partitioning it. So that's the new feature that came into NVIDIA using CUDA. OpenCL had this feature since a long time, where it is called as subdevices. You just take a device and then partition it. So the partition can be either on a NUMA domain, giving you a certain piece of memory and the compute units, and that's how you partition it. So similarly, it's the same as SYCL. As I said, like SYCL draws a lot of terminology from OpenCL. So you have SYCL subdevices. So you have device. If you want to partition it, you call it as subdevices. And there is a terminology called explicit and implicit scaling and all that. Explicit scaling is nothing but a MIG mode where you just chop it up and use it. I would say one needs to pay attention. I mean, don't get so much frightened by these few lines. This is nothing but CUDA set device 0. So one line of CUDA looks like horribly like this. This has improved quite a lot, and it's quite outdated as well. So you could leave out a few lines. All it does is, when you land on a NERSC computer, when you run these few lines, like let's just say the first block, all it does is, on a node, it just gives you the number of devices. So get devices, and you're saying, give me the type of GPU. It'll just give you, and you can see that auto declaration here. It's nothing but C++, and it'll give you a vector of devices. So it's a stud vector. And you just loop over the stud vector and then get all the information. It's as simple as that. So when you log into Perlmutter after lunch and you run this code, for example, you will see 4 GPUs on it. And when you loop over each GPU, you can just query for all information. So CUDA device attributes, I believe that's what it's called still today, can be queried similarly with this. So the motivation behind showing this slide is CUDA, SYCL, OpenCL have a great bit of similarities. It's just any new programming model has a different syntax, right? So one just needs to get familiar with that. So explicit scaling is nothing but you take a GPU, chop it up, and then use it for whatever needs. Or you could just, implicit scaling is nothing but you just take the GPU and use it right away. So the place where you chop it up is right here. So you take a device, which is from a vector. You said create subdevices. And you just gave a condition that partition across the NUMA domain. And that's the property. You're saying, if it is a NUMA domain, partition it right there. So this is the entire story behind subdevices, MIG mode, and in the implicit scaling, you just take the device, use it right away. One should ask the question, what is SYCL queue? And this is the most fundamental, this is the most fundamental entity to touch a GPU, or to submit any work to the GPU, you need a queue. So think of it as like an initialize in COCOS or MPI init. So you need a queue, initialize with whatever GPU here. So here, you take the entire GPU, and then you said, create a queue. So this is nothing but like an initialize, where you take a GPU, and you got a queue. So you submit all your work, either it could be compute or copy, to this queue. It's that simple. So yeah, so SYCL queues provides the mechanism to submit work. And you have context. So many of you might not even pay attention to a CUDA context. So how many of you have heard CUDA context before, or paid attention to? A couple of them. So that's because they are created implicitly behind the scenes. So when you do a CUDA set device, it sets the device. But behind the scenes, the runtime sets the context. So it's the same story is right here, but you have exposure to it. So I will just skip all the details, but I would say that pay attention to the queue. And just to make things familiar, queues are nothing but CUDA streams behind the scenes. So if you're familiar with CUDA stream, entire logic applies to the queue. So queue is always attached to a device, and streams, and why do you use CUDA streams? The main purpose of CUDA streams is to launch asynchronous tasks, correct? So that's the same purpose these queues provide. So asynchronous tasks, and one of the most important thing here is SYCL queues are both in order and out of order. So when you assign some task to a CUDA stream, they are always FIFO. So first in, first out. They're always in a single pipeline. But you have two different options. You could just do an out of order, which is the default, or you could just specify that the queue be an in order, which mimics CUDA streams. So I would say, like, just for the sake of not taking a fire hose of information, pay attention to the queue and just these two terminologies, in order and out of order, which will be helpful in the next coming slides. Before we go out for lunch, I'll just give you a brief overview of the Perlmutter that you can have access to. So Perlmutter is Perlmutter is a machine that is housed at NERSC, LBN, Lawrence Berkeley. So it's still a pre-production machine. So you are the first few people who would be using it, and it's about number 5 or 4 from the top 500 supercomputing architectures from last I've seen. So this is just the information about. You could look it up. The most important information is it has 4 A100 GPUs per node, and it has AMD CPU cores. And the rest of them, you could just look it up later. And you could find more information from this web link. Yeah, one important thing to note here is it's flagged as one of the energy efficient machines. Just before we go, this is just the instructions to log into Perlmutter. I hope you got a chance to get your training accounts before. If not, please do it now. We have about 20 minutes or so. So you could log, if you did not request for a training account, just go to this link, use the training code, fill the basic information, and you will get the username and password. Please save that. Don't close the window. So, and after that, just follow these steps to log in to Perlmutter, and we can go from there. Just take like about 10 minutes or so. How many of you already have accounts on Perlmutter from training? Okay, most of you. Okay, then let's skip this step. So you can log into this. One important thing, I don't know if we have time, maybe we could do it in 20 minutes or so. We'll build our own compiler for SYCL from LLVM. It just takes about 20 minutes or so. The idea here is these compilers are being developed daily. So there are new features and the performance implications that are being added almost every day, if you see the comments. So what we would do is we will get the compiler, build it ourselves, take a small SYCL code, and run it to test it. So you can follow these instructions to get the compiler. The first one is where you can grab the compiler, untar it, and these are the build instructions to build the compiler. And if time permits, we will test it. Otherwise, we'll just do a simple test later. So I would say log into Perlmutter, and I'll do it here as well, and follow these instructions. Just feel free to raise your hand if you have questions or see any difficulties. So yeah, these are the instructions, and these are also available in the Slack channel document.